Hello, my name is Julian from CoinLab at Michigan State University. Today I'm going to present PSAF, a probabilistic surrogate-assisted framework for single objective optimization, where we target the optimization of computationally expensive functions. Of course, I also like to thank my co-author and PhD advisor Kalyanmoy. Let me start by explaining what problem class we are targeting at. So in this study, we were looking at unconstrained single objective optimization problems, where the objective function f of x is time consuming or computationally expensive. We were looking at low dimensional continuous search spaces. Continuous means x is element r of n, with n, the number of variables, being less than 20 in our case. Moreover, we assumed the existence of lower and upper bounds. Next, I'm going to introduce surrogate-assisted optimization and tell you why it's so useful for optimizing computationally expensive problems. For many computationally expensive problems, our evaluation is based on a model or simulation, which means an optimization method calls the evaluate function, which triggers a model or simulation to run, which returns some metrics, objectives, or constraints. The issue is that many optimization methods require thousands of function evaluations, which means if the time-consuming function is called thousands of times, the evaluation time and the overall running time of the optimization method increases. Thus, it makes sense, instead of running the time-consuming evaluation every time, to have a function approximator, with the ultimate goal of selecting new solutions more carefully. For this reason, we use a surrogate. The surrogate is fitted using high-fidelity values originating from the model or simulation, and returns approximations, also referred to as low-fidelity values. The goal of the surrogate is to provide more promising solutions to the optimizer, which are then evaluated on the model or simulation. 3 questions have to be answered when using surrogates. First of all, what should be modeled? We answered this question by saying we have only unconstrained single objective problem, so only one metric to model. What should we model it with? In our study, we use a surrogate ensemble. We use Kriging and RBF with different hyperparameter instances and select the one which shows the least modeling error. The focus of this study is how do we utilize the model prediction during optimization, which we are going to discuss next. Let us start looking at different ways of how surrogates can be used in optimization. In the early stage of surrogate-assisted optimization, people used the surrogate once idea. With surrogate once, we refer to obtaining data points, modeling these data points, optimizing them, and taking the optimum. Obviously, if the optimum of the surrogate and the true function are very, very close, this is a good solution. So this only happens if the surrogate is sufficiently accurate, which might require a lot of data points initially. However, if the surrogate is not good enough, then the deviation between the two optima might be too big and require an adaptive optimization. Adaptive optimization we see as surrogate-aided, customized, and dependent. For example, in surrogate-dependent, we have an algorithm where the surrogate is a substantial part of the algorithm's design. For example, the well-known efficient global optimization idea, EGO, uses Kriging, and the surrogate is a substantial part. So if you take the surrogate away from the algorithm, no algorithm is left. On the other hand, there are surrogate customized and surrogate aided algorithms. With surrogate customized, we refer to you take an algorithm, you do some customizations, and the customizations are still an essential part. For example, is using ARVA, customizing it to be KRVA, a Kriging-based RVA version, where we still have some additional steps that are executed and they're an essential part of the design. With surrogate-aided, we refer to a very simple change which still improves the result. For example, an evolutionary strategy idea where we have 200 offsprings. Now using a surrogate, so let us create 800 offsprings and just take the 200 which are the most promising one. Surrogate aided means we can simply take the surrogate part away and we still have the original algorithm. Of course, the transition from aided to customized is a bit fluent and a bit subjective. However, in this study, we are aiming at a surrogate-aided idea, which is a meta algorithm which can take an existing optimization algorithm and adds surrogate usage to it. In this study, we propose PSAF, a probabilistic surrogate-assisted framework. So let me briefly tell you the goal and the idea behind the framework. On the right-hand side, you see a figure illustrating algorithms for different problem types and efficiencies and computations. The figure is inspired by Goldberg's schema from 1989 targeting genetic algorithms. Here we have different problem types. For example, let's say single objective linear problems. And then we propose a surrogate customized algorithm, which is now specialized for this problem type. However, in this study, we target a robust class of algorithms, let's say all genetic algorithms, and we can add surrogate assistance to the whole algorithm class. This way we have a more generalizable approach, which is broadly applicable. Other things which were important during our design of the framework is that we can use all kinds of surrogates. It's not restricted to a specific type. In fact, as mentioned in the beginning, we are searching the best one out of many different instances. Also, the surrogate error is addressed algorithmically. How our algorithm or framework works, we will discuss next. You might wonder how we define a whole algorithm class. So PSAF is applicable to all type of algorithms that have these two methods, an infill and an advanced method. It's important that the infill method must be non-deterministic. Let us look at some frequently used meta-heuristics, for instance, genetic algorithms. There the infill is the mating. So what happens is we take do a selection, then a crossover and a mutation, and we get new offsprings for the next generation. And the advance, that's the survival, which takes the population, takes the offsprings, merges them together, and does an environmental survival. So basically this is how these two methods are used in genetic algorithms. Let us look at particle swarm optimization, or in short PSO. There, for the infill of solutions, we execute the particles equations having the local and the global best in some way involved and some randomness. The advance is a simple personal best replacement. If the new solution improves the personal best, we replace it. Or let's look at CMA-ES. There we sample from a normal distribution to get new infill solutions. And the advance is an update of this normal distribution over time. So this is 3 examples of algorithms which fulfill the requirements to use PSAF. The idea of PSAF is twofold. First, we have the surrogate influence through tournament pressure, which we do in the so-called alpha phase, and then surrogate bias by continuing running on the surrogate, which we call the beta phase. In the third part, we then either choose points from the alpha or from the beta phase. The alpha phase occurs after the algorithm has been initialized. So in the very beginning, we are generating the design of experiments and evaluate them. We use Latin hypercube sampling to guarantee some space-filling manner. Then we enter the optimization loop. We are calling the infill method of the algorithm, which means the algorithm usually would just do infill advance, infill advance, infill advance. But in our case, we are doing a tournament, which means this here originates from the first infill call. But we are doing a tournament with alpha equals to 3 here, in this case, solutions. So we are calling infill 2 more times, and then we determine the best solution out of the first indices in this example, and send the winner to our new pool. For the tournament, the surrogate serves as a referee, which means the surrogate's predictions are used to compare the solutions, and the best one only survives. What is important here is that we are just looking at the current state of the algorithm, which means just calling infill will not call the advance. For example, for CMES, we will always sample from the same normal distribution but not update it. which means it does only use the current state and does not look multiple generations into the future. This is what we address in the beta phase. So we have the winner of the alpha phase, the variable x. Let's look here specifically at x1. And then we continue running the algorithm for beta more generations. Here beta equals to 5, which creates more solutions. Then we assign each of these solutions to the closest alpha winner. This creates a pool of solutions here, for instance. Out of this pool, we are going to select the best, which tells us the surrogate. In this case, this turns out to be the best solution by using the surrogate's predictions. So finally, we have for each of the alpha winners another candidate originating from the beta phase. Then, with a probability of rho, we either take the one from the alpha or from the beta phase, which means rho determines are we using the one with surrogate influence, not changing the advanced states, or the one from the beta, which calls infill and advance a couple of times and looks multiple generations into the future. If the surrogate is better, then a higher probability of using the beta phase is suggested. We are looking into the different meaning of the variables in our result part. One quick note why we are saying PSAF is truly surrogate assistant. So assuming we are setting the tournament pressure in the alpha phase to 1, basically means we are not doing any tournament at all. And if we set beta equals to 0, we are looking 0 generations into the future, which means this degenerates to the baseline algorithm. However, if we increase alpha, we add more surrogate influence, and if we increase beta, we add more generations we are looking into the future. So this means because it degenerates to the original algorithm, it's a truly surrogate assistant framework. So you might wonder, what are suitable values for alpha, beta, and rho? So we conducted a whole hyperparameter study using CMES as a baseline algorithm. You see here all the hyperparameter combinations and the performance on the most right bar. The baseline approach, as shown on the last slide, alpha equals to 1, beta equals to 0, rho becomes irrelevant in this case, is set up to be 1.0. So we measure how can our PSAF framework improve current solutions. First, you can observe that most surrogate assistant methods improve the performance by quite a bit. Moreover, one can see that for some problems, a larger rho is better, and for other ones, more complicated ones, a smaller rho is better, which means it might make sense to study rho in more detail. For this reason, we propose updating rho dynamically. The concept is based on the R2 score, because our intuition is that if the surrogate is better, we want to have a higher rho, and if it's worse, we want to have a lower rho. So we are using the accuracy of the surrogate to define rho. The R2 score is based on having two predictors. One is the most simple predictor you can imagine, always predicting the mean of all data points, which we have in the denominator. And in the denominator, we have our actual predictor. So what R2 does, it sets the relative performance of the predictor to the most simple predictor, which always predicts the mean, and 1 minus this value. Which means if your model fits perfectly, this will be a 1. If your model is better than the mean predictor, it will be between 0 and 1. And if it's worse, it will be below 0. Because we are having a probability, so we want to have no negative values, so we have a cap at 0, and we replace always using the mean predictor by using a baseline predictor. In our case, a simple nearest neighbor prediction. And as said, now we have the probability property. If the surrogate is perfect, we have a rho of 1.0, so we always use the beta phase in this case. If it's worse than the baseline predictor, then this value here becomes bigger than 1. 1 minus something bigger means our 0 is used, which means we are not using the beta phase at all. And this is actually what we are trying to accomplish. Use the beta phase if the surrogate is good and look many generations into the future, and don't use it if it's not as good as you were thinking. Lastly, I want to briefly talk about the results. So on top, you see the hyperparameter study, which we have shown before in the PCP plot, but as a table this time. And now if we tune our row adaptively, we can see a significant improvement in performance. Because of the time limitations of the video, I'm only going to present briefly the results. We compared 4 different algorithms: genetic algorithm, differential evolution, particle sum optimization, and CMAES, and their PSAF variants with each other, and with 3 other state-of-the-art algorithms on various test problems. First, one can observe that for most problems, the surrogate assistance significantly improved the performance. We have seen this throughout the whole experiment we have conducted. Moreover, one can see that for some problems, the local search behavior could be improved. For example, for sphere 10 dimensions, the local search of LQCMES converges quicker to the exact optimum. This means a local search behavior might need to be included in the PSAF framework in the future. However, our hypothesis that adding surrogate assistance to other existing optimization algorithms is a competitive method to state-of-the-art can be confirmed. For more details about our results, I'd like to refer to our paper, where we have a discussion of up and downsides of PSAF. Lastly, thank you for watching. We proposed PSAF applicable to a broad category of algorithms. Some future studies is investigating the local search behavior, applying PSAF to even more algorithms, and a generalization to constrained and multi-objective problems. Thanks for watching.